Thanks to all of you for coming here today. So I'm Karol Desnos, and yeah, this will not be about astronomy, sorry, and you will have to endure my terrible French accent for 40 minutes. So I will try to do my best to remain understandable. So a brief history of execution times from pipeline choices to Dataflow models. So first of all, of course it's not working. Easy. Yeah, here it is. First of all, where do I come from? So Adam already told a bit about where I come from. So I come from this place in France, which is a city called Rennes. And I'm working in an engineering school. It's a small school compared to huge universities. It's basically a 5-year engineering curriculum, and we have roughly 1,500 students. And I am part of the electronics and computer engineering department. And the city of Rennes is a wonderful city. Here are a few pictures. The animations are crazily slow. So these are a few pictures of the city and the school. And as you can see, the sky is always bright and blue in Rennes, which is absolutely not true. It's like the pictures of Melbourne. They are not taken at the moment, obviously. Yes, Brittany is known as a rainy part of France. So the city is very nice, but if you visit in winter, don't expect this blue sky. Okay. And as a researcher, I am working in the IETR, which is in French, Institut d'Électronique et des Technologies du Numérique, or Institute of Electronics and Digital Technologies. It's part of the CNRS National Laboratory. And I am part of the Vaader team, which stands for Video Analysis and Architecture Designed for Embedded Resources. You know, we have a cool logo, thanks to this wonderful name. So what are my research activities? What do I do? My first research interest is about model-based computer-aided design, and I will talk a lot more about it in the next 15 minutes, let's say. And I'm also interested in image and video coding for machine learning. So here, just in a few seconds, what it means that when you have an image taken by a camera, usually it is encoded, it is compressed before being submitted on the network to try to save some bandwidth. And then it is decoded and it is viewed by a human viewer who is happy with the nice quality of the YouTube video of a cat. And when you have an application where you have a camera that is sending a video over the network for an artificial intelligence to process this video, you actually don't need this very high quality because the AI doesn't care if the video is nice or not. And so here there is an opportunity to compress the video much more violently, much more strongly, and losing some quality of the video, as long as the artificial intelligence is able to analyze the content of this video. And so this is a topic we are also working on in our team, and that I am working on. And I'm also interested in machine learning with the frugal artificial intelligence and tangled program graph, about which I gave a director's lunch talk and a cookies and code session earlier that year. Okay, so why am I here? So I'm ending next week 5 months mobility here in Swinburne University at Technology, and I'm going to spoil the end of the presentation. Here is the result of my work here. Yes, I know, it's wonderful. It looks beautiful. It's the Windows 95 style. I love it so much. Okay, so at the moment, you're probably thinking something along these lines, I guess. So, of course, you are absolutely not right, but I understand. Okay, just a glimpse under the hood, and then I will talk a bit more about why this is interesting. Under the hood, to obtain this kind of a loading bar to a radio astronomy processing pipeline, there are lots of things that need to be done. And I had to put together some memory and timing analysis to build some parameterized model of the pipeline that we are running. I'll also have a way to do some real-time monitoring of the pipeline while it is executed on an HPC infrastructure. And also I need to put together some kind of data flow modeling. And if you have no idea what some of these terms are about, well, stay here. The presentation is about to explain everything, hopefully. Okay, so let's go for it. First, a bit of background. I will talk about what I did before coming here, and mostly since I did my PhD a decade ago. Yeah, a few years, let's say. Okay, so first, what do I work on? I work on cyber physical systems. Cyber physical systems are systems where you have a physical environment. So you have a physical environment with lots of nice phenomena, and this physical environment produces data that you are going to process in a computing platform. From the result of this computing platform, you can interact once again with the environment with an actuator to control, I don't know, the temperature of a room, or to generate some sound or some images, or to control a robot. And these are the kind of systems that I am designing. And now these systems are also interconnected, and so they are usually Internet of Things embedded systems, which are able to send data and receive data through the internet. Okay, these systems are everywhere. We can find them in cars, we can find them for health device, in the industry, and what interests you in astronomy. When you are building a nice antenna, a big antenna, or big scientific facility like the SKA project, you need this kind of system everywhere to process the data that is coming out of the antennas. Okay, why is it challenging to design this kind of systems, this kind of embedded system? Well, there are many things to optimize, many design objectives to optimize when you design this kind of system. But first of all, and which is usually the most important to everyone, and historically it's the most important, we have to have an efficient system. The system has to have a low latency, a good scalability, a low energy consumption, high throughput, a good quality of service, and so on. So this is usually the main concern of developers. But there are many other design objectives. The first one is safety. You need to ensure some real-time properties, sometimes for the safety of the user. You need your system to be verifiable, testable, and resilient to fault. Then you have the security. If you are handling some data, personal data, for example, you need to make sure that the privacy of the data is guaranteed. You also have the cost, which is always a problem. You want the cost of your system to be as low as possible, and you want your system to be upgradable and maintainable easily with a low cost. You want your system to be sustainable. This is something that was not part of the picture before, but today it's something we cannot not think about. So we have to make sure that we build system with a low emission, CO2 emission as possible, with low energy consumption, and so on. And unfortunately, each one of these objectives, the optimization of any of these objectives, is a very complex problem and a research domain on its own. So each design objective taken separately is a difficult problem to solve. And unfortunately, these problems are antagonists. Like if you are trying to improve the sustainability of your product or of your embedded system, you are most likely increasing the cost, which is something you probably want to avoid. Even if you just focus on efficiency, if you try to just improve the latency of the system, it will probably reduce the energy, increase the energy consumption of your system. So you really have to struggle with many antagonistic objectives. Okay, so this is what I'm interested about. I have many configurations of the system to explore to optimize the different objectives, and unfortunately, the configurations do not sum, they multiply, and in the end, the design space that you have to explore is huge. You have millions of configurations to explore when you want to design a system to obtain the best system possible. And what is the best system, actually? If we compare, for example, the sustainability and the cost of a system, you may have many different configurations, okay? One of them is the best in terms of sustainability, one of them is the best in terms of cost, but there is no perfect solution. You always have a trade-off between sustainability and cost. And what's interesting for you is actually to try to find the Pareto front of solution, which are the trade-offs that you want to propose to the system designer and from which they can choose, okay? Okay, so the challenge here is that we need powerful methods and tools to automate and accelerate the exploration of this huge design space. Okay, I'm on schedule. Good. How can we explore this huge design space? And here I'm going to talk about Dataflow. So is Dataflow the savior of the embedded system designers? Okay, what is the Dataflow? The Dataflow model of computation is a way to represent an application, a way to specify an application. In this model, applications are modeled with a graph, and the nodes of the graph are called the processes. Okay, they represent basically a function that is doing some computation. We can also call them actors. Okay. And these process or the actors are able to exchange data through first-in, first-out channels. And to exchange data, they are able to produce what we call the data tokens. Okay, so they consume and produce data that are forwarded to other processes that can consume them and do some useful computation. Okay. Why do we like this model as embedded system designers and also as astronomers for some of you? Okay, we like this model because we have modular computation. We can separate the different processes and they are completely independent from each other. They just exchange some data, which is quite convenient. We have explicit data dependency, which is good to analyze what computation will be triggered at any point in time. The model itself, the model of computation, the theoretical model of computation is implementation agnostic. So if I model an application with this model, for example, I can implement it in different ways. I can implement it in Java, I can implement it in Python, in C, C++, or even in VHDL. Okay, the application model is not linked to a specific implementation language. The model is highly parallel. If you have several nodes that receive or send some data in parallel, then you can run them concurrently on different process elements of your computing infrastructure. The model, the one I'm interested in, which is in this case the CAN process network, is deterministic. Okay? In this model of computation, if you put the same data in the model, you will always get the exact same result. This is guaranteed by the semantics of the model. And the model is analyzable. You have lots of mathematically grounded analysis tool that makes it possible to get some good property about this model. I will talk a bit more about this in a few seconds. It's user-friendly because who doesn't like a graph? And many more advantages, and there is a lot corpus of related work on this topic. Okay, so KPN, the CAN process network, is one of the most famous model of the Dataflow models of computation. It was invented 50 years ago by a French scientist, Gilles Can. And this model is the first of a family of Dataflow models of computation. And now there are many models that have been inspired by this CAN process network model of computation and that changed the rules of execution to create new Dataflow models of execution. I'm doing cosmology now. Okay, among this model, one of them is particularly interesting, the synchronous Dataflow model of computation. This model was invented in 1987 by an American researcher, Edward Lee. And for the same, because it's a popular model, for the same reason, there are many spin-off models that are based on this model and that have had some adaptation of some specialization of the execution rules of this model. Okay, what does this model look like? Synchronous Dataflow is the model I'm mostly working with. Is a model where you have some actors, but with very specific constraints for their execution. Basically, every time you have an actor, you have some input and output ports. And every time you want to execute the function associated to this actor, you need to consume and produce exactly the number of data tokens associated to the data port. So here, for example, the read actor will consume exactly one token on this input and will produce 720 tokens on this output and one token on this output at each execution. This is not dynamic, this cannot change at any point in time. Then you have the first-in, first-out queues. And this model is, the execution of this model is data-driven. So as soon as I have 720 tokens in this first-in, first-out channel, I can start an execution of the split actor. What's even more interesting, as soon as I have 732 tokens in this channel, I can start two executions of the Sobel actor in parallel. I have enough data to start two executions in parallel. I can do it. And so by analyzing the graph, I can know that if I execute this actor once, this actor once, this actor twice, and so on, I can execute all actors at least once and come back to the initial state of my graph where I have no token in any first-in, first-out channel except one in this channel. Okay, this is very interesting. This is something that I can analyze at compile time, and there are many other things that I can do with this model. Yeah, I have no support for this. There are many things that I can do with this model. I can analyze it, compile it very efficiently. I can analyze the model to check if it's deadlock free or not at compile time. I can schedule the computation. I can allocate the memory at compile time. And this is what we are trying to do as researchers with a tool that we have developed that is called Preesm. So, at the input of this tool, the Preesm tool, we have a Dataflow graph like with the synchronous Dataflow model that I just showed, and a model of the architecture, a very high-level, simple model of the computing resources that are available to you. Then these two models go in the front end of the tool, where we do some analysis and some transformation. So we analyze the graph, we verify that it is correct, that it is deadlock-free, for example. We analyze its degree of parallelism, and we do some transformation to try to optimize it. Then we do the resource allocation. So from this model, we can allocate the functions on the different cores of the architecture. We can allocate the memory. We can allocate the communications on the different means of communications of the architecture. And we give back simulation results to the developer, and the developer can control the resource allocation to tune it in a direction or another, depending on the objective that he is pursuing. And this is the front end, and the resource allocation is the design space exploration. This is where you will try to find the best configuration for your needs. Then, when we are happy with the resource allocation, we give our results to the backend that can generate some code that can run on an actual tablet. And we can also run some profiling or some runtime management of the system. So this is what the Preesm tool does. Okay, inside the Preesm tool, what do we have? So we have the Dataflow model, and here are a few outputs, a few interesting things about the input model. First, we can do some analysis, as I already said, to check if the model is deadlock-free. We can also analyze the parallelism of the system and try to check the real-time properties of the system. And check the real-time properties of the system. We can also, with a heuristic model, compute the theoretical minimum and latency and the theoretical maximum throughput that we can hope to have independently from the architecture. Like if we assume that we have an architecture with as many cores as we want, we can easily compute what will be the minimum latency achievable. We can also compute memory bounds. This is very useful. From the Dataflow model of computation, you can say, okay, for this model, I know that I will need between 2 kilobytes and 200 kilobytes of memory to run this model. You will never need more than 200 kilobytes and never less than 2 kilobytes. So it's very interesting as an embedded system designer to have this kind of knowledge very early in the design process. And then we also have ways to try to predict the energy consumption of the system based on the model of computation and on the model of the architecture. Okay, these are the inputs. Then a few words about the front end. As I said, we have ways to automatically optimize and transform the input model of the application. So here, for example, we can do some automated granularity control. We start from a graph. This is a graph designed by the developer. And if we do a transformation that reveals all the parallelism in the graph, here I reveal the 4 execution of actor B and the 2 execution of actor C. So here I'm revealing all the parameters and putting some plumbing in between to make sure that the data goes in the right place. Okay, this is good, but if I had here like 10,000 execution of actor B and 1,000 execution of actor C, I would have a very big number of actors, of nodes in this graph. Very often, this would be too big. For example, if I have 10,000 execution of actor B, but I have only 32 cores available for me, I'm revealing too much parallelism compared to the architecture that I have in front of me. In this case, we can do some automated granularity control. What we do is that we apply a transformation to the original input graph to merge some actors and to control the degree of parallelism. And then when we do the transformation, we have a graph with a limited parallelism, which corresponds to the potential parallelism of the executing platform. And this was the work of Ophélie Renaud, who was here last year for 1 month. She visited the team for 1 month, and she was supervising Ewen Bouvier, who was an intern student from our school and who visited Swinburne last year for 3 months, if I remember well. Okay, there are a few other things that we can do based on the model. For example, instead of having to build this huge directed acyclic graph to map the computation on the available resources, we have a way to build only this input graph and to automatically infer all the information from this huge graph without having to build it. This is something that is very interesting from the embedded system domain side, because by not building this graph, we can divide the memory footprint of the manager of the computation by a factor 33. And we can actually reduce the time taken to do the resource allocation by, we can accelerate it, sorry, by a factor of 7.8. So it's very interesting. Okay, resource allocation. I talked a lot about resource allocation. What this is? The resource allocation consists of allocating computation, data, and communications to the different elements of your computing platform. So here, I will allocate the computation on the different types of core of my architecture. I will allocate the data in the different memory that I have on the chip. And the communications will take the different means of communication of the chip. And there are different strategies that we can use to do that. We can do it offline at compile time or online while we are running the application. And both of these possibilities are supported by the tool. We can use a heuristic algorithm, which will try to find a good enough solution in a very reasonable time. Or we can try to go for the optimal solution, which usually implies trying to solve NP complete or NP hard problem. And so finding the optimal solution is very often not feasible for a real-life problem. We can do a mono-objective optimization, or we can try to optimize multiple objectives at the same time, like latency and energy. And this will give us different solutions. And there are many metrics to observe when we do that, and I already talked about in the first slide, so I will not spend a lot of time on this. What are the targets that are interesting to us when we use Preesm? The first and most important target for us was MPSOX, which stands for multiprocessor system on chip. So when you have different kinds of cores embedded on a single piece of silicon. We also, of course, target the general purpose processors that you have in your computer. We can also target many core targets, where you have hundreds of homogeneous core on a single chip. Thanks to Ewen that was here last year, we can also target graphical processing units. Thanks to Ophélie, we can target high-performance computing infrastructure like OSTAR. And we also have ways to generate code directly for an FPGA. So hardware implementation. So this is what I did before coming here since my PhD. So now the question is, how does this apply to what you do, guys? Okay, so let's talk about Nextflow and let's talk about the one Astronomy pipeline. Okay, still not. Okay, this is a pipeline that some of you know very well. This is an overview of the Celebi pipeline for processing and localizing fast radio bursts for the FRBs. So this is an overview of the pipeline that you can find in the paper on the paper introducing the pipeline. And here you have the top level representation of this pipeline with different tasks that exchange some data. And if I were to zoom on each specific task, then I could have the lower level of hierarchy, which represent another part of the pipeline. Okay, so the first thing and the first very good news for us is that this is definitely a data flow graph. You have some processes that are exchanging some data. And so this is something that we know. This is something that we can work with, and we can try to build a bridge between this representation and the one that we have in Preesm. Okay, this is definitely not an embedded system application, because when you run it on OSTAR, depending on the data set that you are processing, you have between 12 and 24 hours of sequential processing time. So basically, if I were to put all the jobs one after the other on a single 32 cores node, it will roughly take between 12 and 24 hours. And if I just have a look at how much one core processing time I have in this application, I have between 15 and 30 days of one core processing time to execute this pipeline once. So I have lots of computation to do. Okay, and this pipeline is implemented with the Nextflow framework. What is Nextflow? So Nextflow is a data-driven computational computational pipeline. So it's a way to model a scientific pipeline using a kind of a data flow model and to deploy it automatically or easily on high-performance computing infrastructure. And for the next few slides, I will try to make a comparison between what Nextflow does and what Preesm does. Okay, so first, what about the application model? When you model an application with Nextflow, the application model looks something like this. You have a set of files, and in each file, you will define a set of processes, and then you can define a workflow that uses these processes. And then you will connect a few processes with channels, communication channels. So this is how you specify a data flow graph in Nextflow. In Preesm, you have two ways to specify a data flow graph. You can either go with a graphical editor, which enables you to just draw your graph and connect the different edges, or you can use the Hockle model, which is based on OCaml, and that enables you to also describe the graph textually if you prefer. Okay, then what about how does Nextflow works? In Nextflow, so the input model of your application is a directed acyclic graph of your application. So each process is linked to the next, and you can never have a feedback loop in your process. You cannot model like iterative computation in this model of computation. And so you give this directed acyclic graph of processes, where the processes are described usually with Python code or with Bash code. You give that to the Nextflow tool, and the Nextflow tool is running on the host computer, on the head node of the HPC framework, of the HPC infrastructure. And this will analyze the script that you have. It will build the directed acyclic graph. It will generate a bunch of Slurm jobs. It will monitor the execution of the application, and it will execute a few jobs. The jobs will be sent to the Slurm manager, which is responsible for allocating the resources on the HPC infrastructure. And the Slurm manager will actually send the jobs to nodes that will execute the jobs with the requested amount of resources. In each node, you usually have something to support the language used in the process, so a Python interpreter or a C++ binary support. And you usually need to have a Bash interpreter, and very often you also use a container for to make sure that it will work efficiently on the different nodes of your HPC infrastructure. So you have actually quite a huge stack of tools to make it work. As opposed to the, not opposed, but as a reminder, here is the workflow of the Preesm tool. Okay, so what is different about the models and language? The model of computation in Nextflow is a directed acyclic graph, which is dynamically constructed when you are running the application. Okay. What's very interesting is that for some reason, the order in which you receive data is not guaranteed. Like if I have 12 processes that are running in parallel and that are producing some data, the receiver of this data needs to find a way to identify from which producer the data is coming from. There is no deterministic order of data token in this model of computation, as opposed to Preesm, where the order in which you receive data is guaranteed. So, for example, when you have 20 executions of a process, there is a first, a second, and so on. They are ordered, and even though they are not, they can be executed in parallel, and their exact order of execution is guaranteed. Maybe the first execution will finish after the 20th. The order in which the receiver will receive the data is deterministic. It's guaranteed by the framework, which is very convenient when you need to receive some data from multiple sources. Okay. About the language, to describe the processes in the Nextflow language, you can use Python, you can use Bash, you can put your own executable, so you can put C code if you want. And basically, the processes will communicate through files. You will receive and produce files in each process. Preesm is mostly made for C and C++ code, and when you exchange some data, you exchange it through pointers. You receive data through pointers and you produce data through pointers. The toolchain is basically a virtualization stack on Nextflow. You have almost no optimization at compile time when you start an application, but at runtime, you need many tools to support the execution of a Nextflow application. You need Groovy, you need a Java virtual machine, you need Slurm, you need Aptainer, you need Python. All of these tools are needed to support the execution of the Nextflow pipeline. In Preesm, you don't need much because most of the job of the work is done at compile time by Preesm and the C++ or the C compiler. And at runtime, you just need a very simple operating system that supports threads. So it's much more lightweight because it's for embedded system, not for HPC system original. Resource allocation. How does Nextflow do the resource allocation? Nextflow does the resource allocation on the fly. So every time a process is ready to be executed, every time some data is received by a process, Nextflow decides that it should create a Slurm job and send it to one node of the HPC infrastructure. Nextflow is dependence agnostic, so it's not trying to predict what will happen in the future. It's building the directed acyclic graph along the way, and it only knows that it has to execute a job when the job is ready to be executed, not before. Even if from the start of your application, like it is the case for the CLB pipeline, you could actually predict the whole directed acyclic graph from the start based on the parameters and the data set you are producing, but Nextflow does not do it. It just schedules them on the fly. In Preesm, everything is done at compile time. All the mapping and scheduling of computation and communication and memory is done at compile time. So resource allocation, the strategy with Nextflow is fight and do your best. You are competing with every other developers on OSTAR, and you are submitting jobs, and you hope to have the resources as soon as possible. So you are competing for the HPC resources. Basically, and you must also, as a developer, you must also specify how much resource you need for each process. For every time you design a process, you need to tell, this process will take approximately 20 minutes. And you write 20 minutes in your script, and this is what will be requested from OSTAR when you start the jobs. This is what we call the guesstimate, or a wet finger. In French, we would say a wet finger guess, like 20 minutes. And yeah, sometimes you are completely wrong. You can book 2 hours for a job that will actually last for 5 minutes, which happens for most of the jobs in the CLB pipeline at the moment. In Preesm, this is under control. All the resource allocation is based on the profiling of the jobs or of the processes. So you will just first profile the jobs, and based on this profiling information, you can allocate resources as close as possible to what's actually needed. The performance of a Nextflow process is highly unpredictable. You can start the same workflow with the same data set several times, and because of everything that was above, it will the actual runtime will be vastly different from one run to another. So you have a high variability. You have no real-time guarantee, because it can last between 1 hour and 7 hours for the exact same computation. You cannot give any real-time guarantee for this kind of process. In Preesm, everything is highly reproducible. When you start the same execution several times, you usually have a variation which is very, very slow, below 1 or 2%. And sometimes it's even cycle accurate on some embedded system. So you can predict very precisely how much time it will take, which is good to give some real-time guarantees. I'm running a bit late. Okay, I love Slurm. I had never worked with Slurm before, and I had the joy of discovering it while here. And Slurm is great because it does not enable you. Predicting resource availability with the Slurm is very difficult because it depends on what's actually currently running on the HPC infrastructure, and it's highly unreliable, unfortunately. Theoretically, jobs will start faster if they request less resources. If you request less CPUs, less time, and less memory, it is likely that the job will start faster. Likely, but not certain. And it's very difficult to reserve some resources in advance. For example, I know that I have first this process, then a second one, then a third. Well, at the moment, Nextflow is not able to reserve the 3 jobs in advance. It will just first reserve the first one, and once it is over, it will reserve the second one, and then the third. For several reasons. The first one is that Slurm reservation are for administrators only. There are a few options that you could theoretically use, but Nextflow cannot use them. And there is a last option that could be used also, but also only for administrators. So basically, trying to reserve resources in advance is very difficult or impossible with Slurm and with Nextflow.
But can't you run Nextflow inside Slurm? Is that not possible?
Run Nextflow inside Slurm, so
you ask resources in the beginning, the whole.
You pre-reserve a bunch of nodes,
yeah.
So that you are the administrator, right, of this bunch of nodes. I'm not sure.
In this case, the problem is that you're like asking multiple jobs when one is completed and stuff, but you're outside Slurm, right? But if your process is inside Slurm.
Yes, there is a way to create a directed acyclic graph in Slurm, but then you will need to bypass completely Nextflow and redesign the whole pipeline without Nextflow, because Nextflow is highly dynamic. So unfortunately, there is a paper doing that, but to make it work, they had to change the code of Nextflow, and they had to be administrator of Slurm. Otherwise, they could not do it, which is great. Okay, so to summarize what I've just told, I have a problem because I have a poor resource usage prediction, and thus my allocation strategy of Nextflow is not great. I will skip that because I'm a bit behind schedule. And so what are my objectives? The first one is to build a resource usage prediction model for a known pipeline, Celebi in our case. And the second objective is to try to use this model to fine-tune the future execution of my pipeline. Okay, so this is what I actually did here, trace analysis and performance prediction. So this is the workflow that I have built while I was here. So first, I'm starting from Nextflow. I have a bunch of configuration of a pipeline, and I can execute them on an HPC framework, on an HPC infrastructure. When I'm executing a pipeline, Celebi in our case, I can generate, for each configuration, I can generate a report of this execution. I can generate a bunch of log, and I can generate the directed acyclic graph of the pipeline that was executed. This information is very interesting for me. I'm getting some data from this information and building a database of several runs of the Nextflow pipeline. From this database, my goal is to build a model to predict the memory consumption of the pipeline and to predict the execution times of the different jobs of the pipeline. From this model, I can then build a frugal configuration. I can build a configuration that is very close to what is actually needed. So no more 2 hours job that lasts for 5 minutes. Now, using the model, I know that this job with this specific configuration will last for 7.5 minutes. And so I can have a loop toward Nextflow. And for the future execution of my pipeline, I can actually allocate just what's needed based on the model that I have built. I can also take the directed acyclic graph, and from this and from the time prediction model, I can build a Dataflow model that I can then feed to Preesm. And from Preesm, I can do a simulation of the pipeline to try to predict its actual latency. Many languages were involved, a bit of Python, a bit of Groovy, a bit of Java, because otherwise it's not fun. Okay, a few details. I'm a bit late, so I will try to not to be too slow. Okay, these are the inputs that I'm using to build the database. From the HTML report produced by Nextflow, I can extract the execution time of the process, the memory they use, and the number of cores they use. From the logs, I can also extract the name of the different run, because each time you run the pipeline, Nextflow gives a funny name to the run. I can extract the parameters that were used to process the dataset in this run. I can extract the name of the processes. I can extract the aliases that are sometimes given to the different processes in the pipeline. And I put all of this in the database, which is quite big at the end of the day. Okay, what do I do with this database? So these are some info that I can find in the database. I have some processes with their names. I have the name of the run, the name of the pipeline that was run, which includes these processes. So here, for example, I have 2 runs of the Celebi pipelines One was named Angry Turin, and the other one is Nicky Shannon. And for each process, I have, these are the real names for information. These are the execution times of the different processes, and these are the memory footprint that were observed for the different execution. From this model, I can, from this database, I can do an analysis of the variance, the ANOVA method, to try to put the processes in different categories. There are some processes that basically have the same memory, for example, for multiple run and multiple instance. Basically, their execution time or their memory footprint is constant over multiple execution, no matter what the parameter of the execution are. And there are other categories. Some have variation that are per instance. So, for example, here I have 2 instances of the do correlation process. And for multiple run, I have the same execution time. For example, the do correlation. Never mind. The do correlation has the same memory footprint on the 2 pipeline, but between do correlation 1 and 2, I have different memory footprint. And sometimes I have variation per run, but not per instance of the process. And sometimes I have variation per instance and per run, which is the worst category, of course. Then, by having a look at the parameters of the associated to each run of the pipeline, so here I have the parameter for Angry Turin and here for Sneaky Shannon, I can use this parameter to try to do a parameter selection to build a model which enables me to predict the execution time and the memory of each process depending on this parameter. And this is one of the results that I have. Here, for example, I have the expression that I obtained to predict the execution time of one process for different parameters of the pipeline that I'm running. And as you can see, the results are not too bad. I'm using in this case a linear regression to make the prediction, and I tried it on a few new configurations, and it seems to work quite well. Okay, very rapidly, I'm also able to generate a few configurations for the next execution of the pipeline. So to try to allocate just resources that are needed and not more. And here is what I had before. So this chart represents the percentage of time that was used compared to the percentage of time that was allocated. So the lower you are, the worse you are. Meaning like here, I'm basically using, on average, I'm using like 10% of the allocated time for each job running on OSTAR. When I'm using the data from the model, I obtain these allocated time, and to give a bit more readable information, here basically I'm using 6% of allocated time for the jobs on average, whereas here I'm using 82% of the allocated time when I'm running the jobs. So I have a much more efficient usage of the allocated resources when it is built on the prediction from my model. The same is true for memory. And it's even more impressive. Here are the different results. Before using the memory model, I was using approximately 11% of the allocated memory, whereas when I am using the memory prediction model, I'm using 77% of the allocated memory when I'm running the job. So I'm much more efficient in the resource usage I'm allocating. Okay, I'm really behind schedule, so I will accelerate. This is the loading bar that I presented at the beginning. When I start the execution of a pipeline, I also created something that uses the database and the prediction models that I have built to try to predict how much time, what is the current progress of the pipeline. And so what it is displaying is the raw percentage of progress of the execution time, the total execution time of the jobs. And every time a job is finishing, it is updating the progress of the loading bar, and it is keeping track of how much total time is expected to happen. This is not an estimated time of arrival. This is just a progress report to know how much raw processing time is already finished, is already passed for the pipeline. So this is good to detect abnormal and unmodeled execution time variation. The model can be updated along the way in real time. This is not an estimated time of arrival for now, and this is still subject to the varying loads of OSTAR. The link to Preesm, this is a simulation that I'm able to do. So I'm taking the Nextflow graph, I'm building the directed acyclic graph, and then I'm giving it to Preesm. And for a given set of nodes, of 1 core node, 16 core nodes, and 32 core nodes, I can create a simulation of the pipeline to try to predict the latency, the total latency of the pipeline. This is not perfect. So this is good because I can approximate how much time it will take to run the pipeline, depending on the number of available nodes. And it enables some kind of design space exploration for the HPC framework, HPC infrastructure. Unfortunately, at the moment, I'm not modeling the waiting time. So this is not perfect. And I'm not yet modeling the data transfer, but this is something that could be done actually quite easily. Oh, what comes next? Future work. This is almost the last slide. For performance modeling, of course, I would like to be able to build the estimated time of arrival of a pipeline. It would be nice to model the transfer size between tasks. It would be nice to test it on other workflows than Celebi. At the moment, I have been testing it only on Celebi, and so it would be nice to have other workflows to make sure it works well. And it would be nice also to make the number of cores used for each job flexible. At the moment, as a developer, you say, this job will run on 32 cores, and Nextflow will always allocate 32 cores for the job. It's a bit not great because sometimes there is no 32 cores node available, whereas there are many 16 cores node available, and you could actually run it on 16 core nodes. It will be twice as long, but if they are available right away, then it will be faster in the end. And for pipeline optimization, it would be nice to apply all the nice data flow optimization that we can do in embedded system for this Nextflow pipelines. And it will be nice also to have some data flow aware scheduling, so to try to allocate resources in advance. But to do that, we will need to get out of Nextflow and to do something with Slurm directly or with MPI. Thank you for your hospitality. Thank you for bearing with me. Also, I'm a bit over time. And thank you for the warm welcome for the last 5 months. And yes, everything I did is open source. I didn't mention it, but Preesm is open source, and all the code that I developed, the framework that I presented here, is also available on GitHub. And while you are asking many questions, here are a few completely irrelevant number about the last 5 months I spent here.
Thanks, Karol, for very interesting and entertaining talk. Are there questions for Karol?
Yes.
Yeah.
So one of the problems that sometimes we have to, for example, if you're using something like Snake or something, and then running a workflow through them for that, if you ask for the incorrect amount of resources and then it crashes, then you have to like do a manual intervention. Can that be fixed with something like this, which can dynamically then fix and go back and rerun it?
Yes, the model I'm building is already including some safe margin of error. So basically, when I build the model, I have a statistical information about how much time it will take, for example, to run the process. And I'm allocating actually the average model plus twice the standard deviation of this model to try to make sure that for 99% of the cases, this should be okay. And I need to add an extra 60 seconds because of something dumb that Slurm is doing. Even if that fails, and this happens, Nextflow is actually able to recover from it. Every time a process is failing because it was running longer than expected, you have the possibility to have a retry with Nextflow. So it detects that, okay, this failed because it was out of time. And the model, the configuration I'm building, every time it fails, it will actually think, okay, this failed. It might be because it did not have enough execution allocated time. So for the next retry, it will actually increase the allocated time by 25%, and it can retry up to 5 times. So it can actually recover from most of the issues of insufficient resource allocation.
And it's also synonymous for memory as well. Like
for memory as well, yes. Yes, it's actually less critical for memory, because for some reason, when you allocate a job with, I don't know, 2 gigabytes, if the job is actually using more, it does not always fail. Slurm is not very, okay, partly because it's not monitoring, from my experience, it does not seem to be monitoring the memory as closely as the time. And so sometimes you can go over the allocated amount of resources. It's not guaranteed it will work, but it can. The time, it cannot. If you reach the end of the allocated time, it will be stopped.
Questions? Sure.
For Preesm, you said that like it's deterministic, right? Execution and stuff. Does that mean that essentially it always is as slow as the slowest task because you always have to wait until that's finished?
So yes, yes and no. It depends. The way we generate code, we generate what we call self-timed code. So basically, you generate some threads and the communication between the threads using semaphores, for example. So as soon as the data is produced, for example, you have two producers producing data and the consumer waiting for this data on another core. As soon as the data is produced, the receiver will receive it and start its computation. So it's not like we don't build like a schedule with a with a fixed start time and end time for the tasks. The schedules they start automatically when the resource is available, which may be sooner than expected if for some reason the tasks that are producing the data finish earlier. But the scheduling is based on a fixed execution time. So here you can either use the mean execution time of the task or the worst case execution time of the task. Yes.
What happens if the estimated time based on simulations? Let's say if you're actually executing the pipeline, then something goes wrong and it exceeds it, and does it stop the execution in the middle?
So in Preesm, no, it will not stop. It will just be slower than expected, basically. In the way we generate code, even if a task is for some reason lasting, I don't know, 20 times what it's supposed to last, it will just delay the moment it will produce the data, and the tasks that are waiting for this data will wait for the data to be available anyway. So it will be slow, much slower than expected, but it will not fail. If you want to be able to recover, let's say, to re-optimize automatically, then you need to do some kind of runtime allocation. In the pure Preesm code generation, we make all the allocation, all the mapping and scheduling at compile time, so we cannot change it while running the application. There are other ways to do that. We also have a runtime manager that can actually recover from this kind of issue. But because you have a runtime manager, you have an overhead, and you need to make the decision at runtime. So it's for most embedded system application, we actually try to make everything static because you have much more control. You can give some guarantee, and so usually developers of embedded system, especially with real-time constraints, prefer to have things that are done statically. I think there was a push. Yes.
Yeah.
Oh, sorry. Multiple questions. Yes, go.
Okay. I wanted to clarify, you were talking earlier about how the front end of this whole process is essentially merging different actions together. Assuming that the actions are all still going through the same sub-process that makes
Yes.
up. How is it? I want to clarify how that merging actually saves on kind of resources.
Okay, it saves on resources because let's imagine that I have 20,000 actors for 4 cores. Okay, every time I generate, if I map all of these 20,000 actors individually, this means that basically in the code that I will generate, I will have 20,000 function calls, individual function calls, and I need a pointer to exchange data, a specific pointer for each one of these function calls. So I need lots of function calls. The code will be very long because they are just one after the other, 20,000 lines of code. I need lots of buffers to manage because I need all the buffers in parallel. When I do the merging, basically, instead of having 20,000 individual function calls, when I do the merging, I can generate a for loop. So if instead of having 20,000, I have 4 times 5,000 calls, then I just generate 4 loops, each of which will be executed 5,000 times. And I just generate one output buffer basically for each loop. So the code will be shorter, and the management of communication will be simpler, because when I have 20,000 calls, I may need 20,000 semaphores or ways to communicate that, okay, this actor is ready and it's producing data from for an actor on another core. So I need 20,000 ways to synchronize 20,000 actors. Whereas when I do the merging, I just need 4 semaphores to synchronize the different cores. So the code is simpler, and the amount of resource I'm using is also simpler.
Did you have a quick question?
Yes. So getting to the idea of like maintaining codes and not crashing them in the middle. I just had the thought about, for a system like OddsStar, where you have a wide number of users who all want their code to run now.
Yes.
Does that mean that people have to wait longer? Or is there like an aggregate win in everything running more efficiently?
So you mean in case you? I'm not sure I understand. In case you.
So if you right now in the current system, if your code stops running, then Slurm runs the next thing. And so if you're waiting in line, you're running. But I'm asking, so if it doesn't crash because it's in principle better for that user, then but it runs slower. Does that mean the person waiting in line waits longer?
Yes.
Yes.
Yeah, because if you are not liberating, freeing some resources, then everybody is waiting. It's also what's also interesting is that at the moment, if you start a job on OddsStar and you have a look at the SQ, you can actually display the expected start time of the different jobs, and it's often completely wrong. Like you are waiting for 32 cores to be available, and very often it will tell you, "Oh yes, it will be available tomorrow." Okay, I will have to wait, and 2 minutes later, oh no, it's okay, it starts running, because for some, we are part, the Celebi pipeline is also part of the problem, because every time we run the workflow, we allocate 300 jobs that are allocating 2 hours each and are using only 5 minutes each. So we are actually part of the problem, because Slurm is just saying that, okay, I have this huge number of jobs to schedule that takes a lot of time. So it will tell everyone else, okay, we'll have to wait for 1 day before you can be scheduled. So this is also why it's interesting to have a better resource allocation. It gives better prediction to everyone that, okay, you will start in 10 minutes, and it's actually very credible that it will be.
I'd like to see like a sociology experiment. And like, are people actually happier when it runs unexpectedly soon?
I hope so. I was certainly happy with the few optimization. Okay, at the beginning, the basic version of the Celebi was mostly running in 5 to 7 hours. And with the frugal configuration, I'm usually able to achieve every run in 1.5 to 2.5 hours. So for me, it's a huge improvement. I'm happy when the workflow finishes faster.
So I was going to take Chair's prerogative to ask the last question, but it's already 11:30. So if you want to know what I want to know about what this matters for the SKA, you'll have to come to lunch. So come and let me know if you'd like to come to lunch, and please join me in thanking Karol again.